Welcome back, Senior Devs. Sean Cannon here. In this lesson, we're going to talk about scalability. So first off, what is scalability? Well, it's essentially how well your application can accommodate growth. There are several areas of growth to consider as you are architecting and engineering your project, and it's important to understand your market cap and load potential early on so you don't end up wasting hours unnecessarily over-engineering something. So what are some examples of growth? Imagine you were building an internal application for companies who will deploy an instance of your app inside their own data center. You can infer that the user cap will likely be the number of employees in the company, past, future, and present potentially. Walmart is on record for having the most employees in the world at 2.2 million, which is actually not that bad. Any mid-tier database like MySQL or Postgres can handle a few million rows in a table, no problem. So your bottleneck is going to be the transfer and display of the data. You wouldn't want to select all 2 million users at once, and you certainly wouldn't want to display all 2 million users at once in the UI because you'd crash the browser or whatever client you're using. If you knew from day one that you were building your project to support 2 million users, you'd most likely accommodate for all this from day one. Simply adding pagination and ensuring users table has appropriate indexes solves this problem. You could even use the database for fuzzy text search and get near real-time autocomplete on 2 million rows with MySQL. Let's imagine for a minute that you actually built your app for local businesses who have 50 to 100 employees and didn't need to add any pagination on the user management screen. The app works fine for months, and you start growing your business and securing larger clients. And imagine you land a health club chain with 30,000 employees. Your user management screen freezes up and offers a terrible user experience, so you have to rebuild that page to support things we talked about like pagination and indexing. This is a very common scenario. If it's not users, it's orders or a ledger of some kind. Anytime you collect data over time and display a list of data, your app is growing, and it should accommodate this growth by defining the UI and API capacity early on. If those capacities exceed your projected stored data capacity, then you shouldn't need to accommodate for growth. In our list scenario, pretend you're making a music library application. A safe growth assumption might be that your user could eventually have millions of songs in their library, but only a handful of playlists. You could decide if you want to keep the playlists feature simple, or if you want to leverage the patterns and consistency and enable pagination for even very small data sets. Neither is a better approach, though I'd personally recommend being consistent because redundant consistency rarely hurts the app. Typically, the product team will own these decisions on the UI and UX level, but at the API and database level, you need to think ahead. Let's shift our perspective now and imagine that this application isn't deployed to corporate data centers, but is a multi-tenancy application, so it needs to accommodate all company employees in the same database. Our growth potential just skyrocketed. You don't need to look any further than LinkedIn, which has over 750 million users. When you start getting close to or exceeding billions of records, the game changes dramatically. If your application grew from even 2.2 million users to 750 million users, your scaling decisions aren't narrowed down to things like pagination. You have to start considering data migration to an enterprise database or another database engine entirely. Migrating from Postgres to Oracle isn't the end of the world, and I wouldn't ever recommend Oracle on smaller systems anyhow, but you need to have it in the back of your head whether or not the migration is inevitable so that you can make the decision early on that will support this migration. For example, if you are using an ORM which doesn't offer Oracle support, you'll need to refactor a large portion of your code when you migrate, which adds a huge risk to the stability of your project. If you're using raw SQL for your queries, you'll most likely need to refactor those queries to change a few keywords and syntax patterns to be Oracle compliant. It's often okay and best to punt these decisions, and rest assured, you won't be alone in the room making them. Migrations and refactors like this take months and involve multiple teams. Just make sure that the multi-team several-month migration effort isn't required because of something you missed. If you went down some rabbit hole with your code and architected the project into a corner to support a record cap of 15% of the project's growth potential, then your product and executive teams will not be happy with you. The next area of growth that we need to account for in our projects is network load. I don't really mean load at your ISP or in DNS, but really once the packet lands on your server, does it need to wait in line or can it be processed immediately? Ultimately, we're talking about user concurrency. How many users can engage with our application at the same time? This is a typical challenge for websites and online games, and the simplest way to support this is load balancing. It's funny how long it took websites to catch on to this concept, because even really old games in the late 1990s like Ultima Online and EverQuest had multiple servers. Each server had a player limit, and once a server started reaching that limit, the game companies would deploy a new server with a new name and encourage players to either migrate characters over to the new server or encourage new players to sign up on the new server. In the web world, it's much simpler for the end user because load balancing happens behind the scenes. Most of you taking this course likely work for a company that has a product deployed somewhere in the cloud: AWS, Heroku, DigitalOcean, Azure, GCP, and so on. Even with these services, it's possible to bottleneck your application, so it's important to understand best practices and the challenges you're going to be trying to solve. You could spin up a DigitalOcean droplet or an AWS EC2 instance and run your entire website on it, and for smaller projects or static corporate landing pages, this is often all you need. If you have a SaaS application though, you need to assume that one instance is going to be overloaded by too many requests. Even servers like Nginx will bottleneck with too many requests, and often your database will bottleneck with too many connections. It's important to define early on how many concurrent requests are allowed and how you will accommodate several times that. AWS offers a service called ELB, which stands for Elastic Load Balancer. You can create an auto-scaling group, so throughout the day as your website receives more traffic, AWS will automatically spin up more instances of your app, and as traffic decreases, it'll tear them down to save you money. This mindset is fantastic, and all you need to do when you're in is write your code in such a way that it can be part of a cluster. For example, a monolith website on a single server can use sessions in memory and have internal pub/sub mechanism because everything is tightly coupled. The moment you spread your code out across multiple servers, you can no longer have state persistence on any one instance. A typical user making 2 requests might hit 2 instances of the API, and instance 2 won't know that the previous request hit instance 1. This is important to consider when handling authentication, authorization, and state. I typically solve for this by putting state outside of the cluster in Elasticache or on a separate Redis instance for smaller projects. Even working locally, I always assume my code can't own the state, and it might need to be deployed as part of a cluster behind a load balancer. Deferring ownership of the state allows me to both scale my application and scale my state mechanism independently. If all of this sounds complicated or overwhelming to you, the first step I would recommend is to reach out to someone on your DevOps team and just chat with them. Ask them how you could make their lives easier with your code, or frame it another way and ask them how the application is currently making their job difficult, and there's a really good chance they will list off some things in line with what we're discussing now. The next area of growth is system load. A lot of this will be solved by the load balancing approach from the previous topic, but it's common for computation of data to slow down over time as data accumulates and the server is doing more things. Generally speaking, it's most often better to scale horizontally rather than vertically, meaning spread the load out among multiple processors instead of making one processor faster. It's not always reasonable to keep spinning up EC2 or ECS instances when you max out your CPU. Sometimes we want to identify our CPU bottlenecks and see if we can extract the processing for this one thing completely out of our server, for example in a Lambda. If we can defer this particular step to a third-party service entirely, even better. A good example of this could be like a virus scan. If every time we upload files, we need to scan them for viruses before we store them, that can create a bottleneck. We want this step to be separate from the uploader, typically as part of a pipeline if possible. If your project's core competency is not virus scanning, then find some service that can pipe the file through an OpsWat instance or something. However we abstract this computational load, we want to use non-blocking flow. Instead of forcing the user to sit there watching a spinner, we return some messaging to the user immediately, letting them know the process is happening behind the scenes, and we will notify them when we're done. As projects grow, the product team is going to start wanting to add new features, and it might be up to you on where to put them in the code. If we use our previous example, imagine you had created an image uploader feature, and then the product team tells you that they want it to support video upload as well. If the uploader was coded very specific to images, then you'll need to have a bunch of redundant code also for videos, or you'll need to refactor the image uploader to be a general media uploader where the type and properties are passed to it based on the file being selected for upload. Maybe once it's uploaded, you have some code that's generating a thumbnail. Well, that code won't work the same on a video. You probably need first find a frame in the video or allow the user to choose a frame, and then your code will extract it, potentially resize it the same way you resize an image thumbnail, and so on. There's going to be a utility logic fork at this step. You can see how simply adding a second media type caused a lot of change requirements. Imagine 2 months from now, the product team also wants to support uploading PDFs. If you keep having to refactor this code, then it's not scalable. In object-oriented programming, you would want to make an interface and create separate classes for each type of file that need to be uniquely handled. In functional programming, you'd want to leverage something like the strategy pattern we've talked about before. Static assets are essentially fully renderable pieces of data that exist on the system, regardless if anybody is requesting them, and are delivered the same way every time. Because they don't require any code or processing when fetched, they don't need to live alongside your codebase, and we can use this to our advantage. The most common static assets are typically the images that make up your user interface, be it a website, a game, a mobile app, and so on. Some other examples might be background music, a sound file, an intro video, or maybe some legal documents or a PDF for your press kit. For remotely fetched static assets like images on a website, there are a couple things we want to consider when deciding where they should reside and how they should be delivered. Ideally, we want the assets to live off the application server so the server can focus all of its power on processing code and handling network traffic to internal subsystems like a database or cache. We also want to keep the overall size of our application servers as small and tidy as possible so deploys and container management is faster and simpler. For example, we may need 15 instances of our application server to handle high traffic at some point, but we probably don't need 15 copies of our logo. A common approach is to put all of the assets in a storage service like Amazon S3 and then put some access rules in front of it through something like CloudFront. Another service like Cloudflare also offers static uploads for images and videos, which can be accessed through an API. Wherever we put these assets, we want to leverage a highly trusted domain that doesn't send any cookies along with the binary. In our system then, we simply store a reference to the remote asset. I highly recommend you keep proprietary nomenclature out of the references. Store just the file name instead of the fully qualified URL to its location, say in Amazon S3 for example, so that the files could be uploaded anywhere with the same name and we can infer its location through a config or environment variables and strategies. For assets, try to land in a place where if you do change your mind and you want to move your assets to another service, it won't require you to change thousands of records in a database or thousands of lines of code. As projects grow in features and complexity, so typically does the need to expand the dev team to accommodate all the new work. I've seen teams grow from 3 devs to 15 devs in a matter of a month, and it was basically up to those 3 devs to wrangle in all the other 12 devs to make sure it didn't turn into the Wild West. As senior devs, we need to make sure the codebase is set up in such a way that it tells us exactly how it wants to look and behave, and set crystal clear expectations with the new devs that the ultimate goal for the project should really be that we can open up any random file and have no idea who authored it. If you find yourself saying something like, "This is definitely Dale's code, he's the only one using for loops," then Dale's hurting the project. Let me give you a loaded example. Imagine you're pulled into a project as a new dev and you notice 2 files. One is get_users and the other one is get_orders, but it's in camel case. The get_users uses a promise chain for its asynchronous data retrieval, which happens to be a SQL query to a Postgres database. The promise chain includes a catch handler and returns a system-specific static record not found error referenced from a constant. The other file is get_orders, which is the camel case one, and it uses async await instead of a promise chain, and it uses an ORM called Sequelize to fetch data from the Postgres database. There's no try-catch block, and so any error that's returned is the Sequelize error. You're given a ticket, make an API to get products from a Postgres database. Well, what do? Do you copy the style of the get_users or the get_orders, the camel case one? Do you ignore both and make your own, which could be some hybrid of the two, and it's completely original? Do you embrace the chaos and name your file get-products? My point here, of course, is that the convention hasn't been established, so there is no clear direction for the implementation details. Tools like linters and static analysis can take care of a significant portion of your coding conventions, so if you don't want to carry the burden of enforcing the rules, try to automate this as much as possible, as early as possible. Ultimately, get the rules, patterns, and standards in place before building any application logic, and the project will be able to scale, grow, pivot, and typically outpace the product roadmap, thereby boosting dev morale and reducing dev stress. That wraps up this module. Keep growing, and I'll see you in the next one.